All right, hi everyone. So we've been working on compound interest. Okay, we've been working on compound interest. And that means whenever we make money, we're going to make money off that money and the interest to get to our next level. So we're going to be making money off our interest, which is good because at every step along the way, we're making even more money. It's almost like an avalanche. A little snowflake pushes snow around it to become a bigger snowball, and it pushes snow around to become a bigger snowball, and then in a sense avalanches. Okay, so let's look at our original problem. Let's say we have $1,000. Okay, and let's do simple interest first. Okay, and the basic idea is if I want to do this by 1 year, 1 plus, let's give ourselves 0.05, so 0.5%, so 5%. And let's just give ourselves 1 year. Oops. 1 year. And this gave us nicely 1,050 bucks. And we said that we can carry this over several years. What if I want 10 years? The problem ends up to be 1,000, 1 plus 0.05. And then since we're going to multiply this over and over and over by 10 times, we just put a 10 on top. We have this. We're going to go ahead and type this in a calculator. Let's go ahead and pull up my school calculator here. Not a school calculator, but Desmos calculator. Not even Desmos. This is just a calculator. 1,000 times parentheses 1.05 exponent to the 10, close it, and then equals, and we end up with $1,628, which isn't bad, right? 10 years, you almost, I guess you multiply by almost 1.5, right? So we're making money off our money, and this $600 extra came from nowhere. That's right, $89.89, right? This $620.89 came from nowhere. What? It came from me building off my principal, my original amount. Principal is a word for the original amount, plus the interest I made at every year along the way. After my first year, I had extra $50. After the second year, I had extra $50 plus the interest on the $50. And then the next year, I had another $50 plus the interest on the $100. So every time I made money, that interest compounded, right? That's what they call it, compound, because it's building on the previous version, okay, previous iteration. Now, we could show what happens. What if I end up saying, I don't pay you once per year, simple interest. I'm going to pay you an n time amount, okay? I'm going to say let's do n times now. In this case, we're going to do semi-annually. How much is semi-annually? That means twice a year. Okay, so our n value is going to be 2 here. So we had a different formula for this one. Let's go and actually rewrite. I'm sorry, I should rewrite the first one. It's A is equal to P 1 plus R to the T. That's what we were working with our little simple interest, 1 time a year. And then if we say you're going to get paid out multiple times a year, will that actually change? Mr. Ko, you're still getting 5% per year, even if I pay you every 6 months. Well, remember, if I pay you 6 months, you get to build money off that 6 months interest sitting there in my bank account. So we get to compound more often. If I pay you your profit early, if I give you allowance early, you can make money off that allowance. So here we go. Our formula here is A is equal to P 1 plus R over N to the NT. Now, how do you remember this formula? This formula looks very crazy. And there's a actual reasoning behind it. If I pay you twice a year, don't you get paid twice as many times? So in 10 years, instead of getting paid 10 times in 10 years, you get paid 20 times in 10 years because I'm paying you twice as often. I'm paying you semi-annually. Every 6 months, I pay you once. So let's take our first year. In January, I put in my money. In July, I get paid out that money, my interest, and then I get to accrue interest on it till December, and I get paid out again in January. So I get paid out twice. And then are they going to give me the full rate? No, it's going to be here. It's going to be 0.05, 5%, but we're going to divide that by 2. This same n is equal to 2 value, right? So I pay you half the interest now, and you'll accrue the second half of the interest on the next 6 months. So not only do you get paid more often, but we cut the interest in the number of partitions in half in this case. So A is equal to 1,000, 1 plus 0.05 over 2 to the 2 times 10. Now, just to make, for simplicity's sake, when I'm typing this in the calculator, sometimes you don't want to break this apart because this is kind of hard, especially the decimal values. You don't want to lose any decimals because sometimes the decimals can be really weird. But you can make this easy by calling this 20 on top. 2 times 10 is 20, right? So let's go ahead and type this in my calculator. I'm going to type 1,000. If not, you can actually type 1,000 at the end. But no, let me show you how I do this in case I make a mistake. Sometimes you type stuff out and you make a mistake, and writing 1,000 and then making a mistake would be a waste of time. So I'm going to write 1 plus 0.05 divided by 2 equals, right? That's our decimal. We're going to take this xy to the 20th case. And then now we can multiply this new number by the 1,000 in front. That's like the safe way of doing it. A is equal to, so you would type this part first, and then this part, and then this part last. That's how I would type it in case I wanted to, in case I know I'm going to make some typing errors. So our actual value is 1638.6 rounding up to 62. Now, is this more or less than our previous amount? Well, let's take a look. If I paid you only one time a year, you would get $1,628. But if I pay you twice a year, just the number of times I pay you, I'm going to make an extra 10 bucks. You might say that's not a big deal, right? Making extra 10 bucks is not a big deal, but I'm making an extra 10 bucks without doing any extra work. Let's go to kick this up a notch. We can want to say every 6 months. Why don't I pay you every month? Let's do that. How would this change if I pay you every month, monthly? Here's our monthly. That means our n is equal to 12. So A is equal to 1,000. 1 plus 0.05 over 12 to the 12 times 10, which is in this case 120. Now, I want to tell you this right now, the calculator steps are no different. By me saying 12 or me saying 2, it isn't actually any extra work on the calculator. We're at 1 plus 0.05 divided by 12 this time. See, equals, that's our decimal. As you can see before, it was like 1.025. Now it's 1.0041 because I'm paying you more often. That means your interest is less every month. We're going to take this to the 120 power because I pay you 120 times over 10 years. And then we multiply this by 1,000. So we end up with 1647.01. Is that much of a difference? No, between me paying you once every 6 months to once every 12 months versus once every year. Sure, versus once every year, you made extra almost $20, didn't you? From 1628 to 1647. Sure, that might not be a big deal. But let me tell you in the grand scheme of things, this was only for $1,000. What if this was for $1 million? What if this was for $1 billion? What if this was a fund that was a $1 billion fund? I had $1 billion that was being reinvested. Would a couple of, in this case, $20 matter if this was $1 billion versus $1 million? Well, let's see. A billion is, real quick, a billion is 100,000,000. That's a billion. So we would add 6 zeros to our 20 here, right? 1, 2, 3, 1, 2, 3. So for $1 billion, this would have accounted for $20 million. You might not care, but for me, $20 million, I'll take your scraps, no problem. And what we're looking at here is, what about credit cards and financial institutions? Do they look at it as per month? Do they look at it as per year? Do they look at it per day? Now, for financial institutions, when you get something called a CD, it's called a CD at a bank, and that's called a certificate of deposit. You are promising that you're going to leave money in the bank, let's say for 1 year, and they will pay you out at the end of the year, or they will give you a total interest rate at the end of the year, an APR. But your credit card, do you know how your credit card calculates how much you owe? They don't do it by the month. It seems like they do it by the month, but they actually do it by the day. Credit card companies, Credit card companies will charge you your interest. They won't wait till the end of the month to charge you. They will charge you on a daily rate. So let's look at how this would affect. Would it affect it that much? Because it doesn't look like we're changing that much, but every penny counts. So let's say this 365. N is equal to 365 days per year. A is equal to 1,000. 1 plus 0.05 over 365 and 365 times 10. Okay. So on the calculator, does it really cost me more time? I'm going to type in, instead of writing 12, I'll write 365. Sure, it's going to take me like one extra button push. Let's go and do it. 1 plus 0.05 divided by 365 equals, we're going to take this, look at the percentage rate. It's not even 1%. It's like 0.0001. We're going to take it to the xy. What's their exponent? We said it's going to be 3,650. 3,650. Why is it so large? Because that's the number of days we're paying. That's the number of iterations you're going to get paid out. And then we end up with A is equal to 1648.66. Now you can see every time I keep adding another level, right, of the number of iterations from months to days, right, I'm not really gaining that much. So they'll hit a point where I'm really not gaining much at all. Sure, I'm paying you more often, but every day the interest rate is so small. If I took 0.05 and divided this by, again, 365, your daily interest rate is 0.0001. That's a tenth of a percent. No, that's 100th of a percent, right? 100th of a percent. This is so minuscule. So what happens is, even though I'm paying you more often, 3,000 times, each of those times is like an ant punching you. It doesn't matter, okay? Now, what we're getting to today is, what if I paid you continuously? Now, this is our lesson for today. What if I paid you continuously? Okay, we paid you twice a year. That's a big gap. I paid you once a month. That's 12 times a year. That's still kind of a long time, right? You had to wait a whole month. What if I paid you every day? Now, what if I paid you every second? What if I paid you every fraction of a second? What if I just constantly paid you whenever I got money, I just put that in your bank account? What would that look like? And this is our formula called our continuous formula. And it's going to be A is equal to P e to the RT. A equals to P e to the RT. Now, E is our constant. E for us is approximately 2.7, blah, blah, blah. If you guys remember pi from geometry was 3.14. And this idea of being paid out continuously is this E, 2.7. Okay, so if I took this number here and I just kept paying you over and over and over and over and over, this same exact rate, okay? I divided it by an infinitely many times. This would give us our 2.7 number. So let's see if this works, if this even comes close to what my number was. I paid ourselves 365 days. Now, what if I paid you continuously? Will it be so much more? Let's go try it. A is equal to our principal, which was $1,000. E to the rate of 0.05. Remember, that's our rate. And the time period is 10 years. Okay. So this equation seems a lot easier than our last equation, though E is new to us. E is this exponential, okay, the exponential, right? This exponential, we just call it E, right? Literally, we just call it E. And this formula is used in physics, it's used in population variation, it's used in anything that has to do with something growing. If it is a continuous model, we can use this. Okay, here we go. So all you do on your calculator is, I'm going to do this first. Okay, let me use a different color actually. I'm going to do this first. Okay, I'm going to do this first. Then I'm going to multiply this by 1,000. So now on my calculator, you have to actually type this first, this exponent part. So 0.05 times 10 And then I'm going to just hit E, and I'll E this number. Oh, actually, no, wrong one. Where does it go? This E, I hit the wrong one, I'm sorry. Different calculators, different things. Okay, 0.05 times 10. And then we're going to use it, E to the X button, E to the X. And that gave us 1,000 times 1.64872. We times this by 1,000. And we end up with 1648.72. Now, is that a huge difference versus what we had previously? That me, and I was paying you every day. Look here, this is my daily rate, and this is my continuous rate. And the answer is no, there isn't a big deal. You know, this is 6 cents worth of difference. And the idea is that we are approaching this limit. There hits a point where, sure, I can pay you more often, but it's not going to make a difference anymore. And sure, I can do the calculator work one more time. But if we hit a point where it doesn't really matter anymore, and that's just continuous, we hit our limit, and the limit is being paid an infinitely many times. So you might think if you get paid an infinite many times, it's of course going to be more. You're right, it is more, but it hits a limit, and it's not like we can make extra iterations from that. Okay. All right, so on my calculator, let me just show you guys one more time. On my calculator, if you guys have a nice calculator that says this, you have an E to the X button like that, excellent. You can just type it as you see it. That you can just type it as E to the 0.05 times 10. Here, you can type it on that little box button, sure. But most calculators, which are under $10, you're going to have to type the exponent first. So 0.05 times 10, oh, I didn't read my writing. 0.05 times 10 equals, and then we're going to E to the X that, okay? So you have to write the exponent first, and then you E that number. And then we can multiply this by whatever numbers we have, by 1,000. Okay. All right. So let's look at another problem. Okay. Let's say you opened up a savings account. Okay. A savings account is, we'll start off with a principal of $800. Okay. Interest rate is at a nice, generous rate of 15%. And we want to compound this continuously. Okay, this is a continuous problem. And we are aiming for a time of 8 years. Okay, so what happens after 8 years? How much will we have after 8 years? So this continuous model, remember, it's easier. It's A equals to PERT, P R to the T. Does not look like PERT. A is equal to PERT. Principal, E to the rate times time. So A is equal to 800, E to the 0.15, and the time is 8. This is it. You just have to know how to plug this in your calculator. Okay, so why don't you guys try practicing and plugging this in your calculator, and then you guys can type in the chat what your answer is. Okay, hi folks, sorry, the recording got cut off. But on our last answer, we said it was going to be $2,656. That's us saving up continuously over 8 years. So we went from $800 to $2,000. We almost tripled our value. Okay, so that was a great rate. Thank you to those who participated. We're starting this next one about population growth using the same idea here. And this is a skill that we're going to use to predict what the population will be in 2020, except we're missing something. We're going to talk about what we're missing right now. So let's say the population of Coville in 1970 is 40,000 people. And in 1980, the census said we have 42,000 people now. So we increased by 2,000 people, whether that's by people migrating or immigrating to Coville, or maybe birth rates. So, you know, it's not that huge of a growth. You might say, hey, what's the big deal? Now, towns have to think about what are they going to do with these 2,000 people? Where are they going to house them? Are there new are there new buildings being built? Is there a new place that was developed? What about sewage? What about electricity? What about the traffic lanes? You guys live in LA and you can see that there's traffic everywhere. There seems like there's too many people for the number of roads we have. And that's all about planning out into the future, saying, hey, if we're going to have an increase in population, we have to have more water, more electricity, more housing. So pretty much all the problems that we have in California right now are this idea of estimating the number of people that will be here and how do we plan for it. So we're going to make an estimation right now about how many people do we expect to have in the population of Coville in 2020. Now, let's look at this. Is this going to be a compound interest problem? Well, kids have kids, families have families, right? They're going to invite people. Maybe there's more work. The idea is that the more people, more jobs. That's what we're thinking, right? So yes, this is going to be compounded. But is this going to follow any type of like, are people just going to move here every January? Population increases every January. Does population increase every month? Does it increase every day? It's this idea of this continuous population. So whenever we're dealing with models that seem that there's no exact date that the growth happens, like a bank account, simple bank account, we're going to use this model of P equals E to the RT. Oops, sorry. Whoops, A. Whoops, I totally misquoted that one. It's A is equal to PERT. I'm not sure I wrote the equal sign. Let me fix this. A is equal to PERT. Now this formula we use for banking can be changed by just changing the variable. We're going to call this population. The final population is equal to initial population, e to the RT. In physics, you're going to use the letter n, right, for mass. So this equation is used in all these different sciences and all these different ways in math. We just change the variable. Now, a couple of things that we want to talk about. What do we know so far? Let's look at our initial conditions. We're given this right here. We're given in 1970 to 1980, and we're given the population growth. But were we given the rate? And this is always what's missing, almost always what's missing, is that we are missing the rate. So let's go ahead and fill in what we know. We know that the final population is 42,000. We know the initial population is 40,000. E to the R, we do not know what the R is, but we do know it took them from 1970 to 1980, 10 years to get there. Now, what we're doing here is we're kind of trying to come up with our rate, sometimes they call us the K value, right, for our model. We don't know what it is yet. They didn't tell us their growth rate is 2%. And this is kind of how they figure out what the growth rate of, for instance, California is, or what Texas will be, or Florida is. We saw a couple of examples of Florida and Texas here. You can see that their populations are growing. Now, they themselves have to plan, just like California had to plan, for this huge influx of people. Do they have enough power for them? Do they have enough water for them? Are the roads big enough? Do they have housing for them? If you don't have enough housing, what happens? Housing prices shoot up. And then you end up with a housing crisis. So here we go. How do we solve for our exponent? Now, I want to ask you guys this question, this general question. How do I solve for exponents? What do we learn that we use to solve for exponents? We use this to solve for exponents. And hopefully you're saying logs. We use logs to solve for exponents. So let's go ahead and start cleaning up first. Let's get rid of the 40. So the 4,000, I lost a zero there. The 40,000. So it's 42,000 divided by 40,000. If you want, you can get rid of the zeros if you want. Is equal to e to the r times 10. Now here is where our skills come into play. We said, how do we solve for exponents? We use logs. Now, which special log do you guys remember that we use for e? Which special log do we use for e? And then we're going to use natural log. Okay, we're using natural log on both sides. 42,000 divided by 40,000 and e to the r 10. If you guys remember what happens to natural log and e, they cancel each other out, and we're left with natural log of 42,000 over 40,000 equals to r times 10. Now, this is a calculator work. We're going to go ahead and calculate what is the rate by solving for r. On my right side, I'm going to type the 42,000. divided by 40,000 equals, and we're going to natural log that. Okay, and then we're going to divide this number by 10. We end up with a rate of 0.004879. I'm going to actually take it all. I want all of it because population is going to be a big deal for me. Okay. Now this is the growth rate of Coville. Is it really that high? Honestly, it is only 0.4%. It's not that high. Nobody wants to move to Coville. Everyone's moving to the big city. But that's fine. Now, how are we going to predict? We're going to now use our initial. Take a look here. I'm going to use my initial, and we're going to go to our final date from 1970 all the way to 2020. Now, how many years is it from 1970 to 2020? The time period that we're trying to push it to is 50 years. So using that initial growth rate of 0.4%, okay? Or 0.004, decimal point 0.004, we're going to use that as our model and give us an estimation. What would it look like 50 years in the future of that? So here we go. We have our rate is now, we said it's going to be 0.004879. I'm going to take as many decimals as I can steal. We have an initial population at 1970 to be 40,000. And then our final population at 2020, which is what we're looking for, is what we need. The number of years it takes us to get from 1970 to 2020, that's going to be 50 years. Now we have everything we need to set this up. Let's do our P is equal to P naught e to the RT. Our final population in 2020 is equal to our initial population of 40,000. E to the rate is 0.004879. We're going to give ourselves a nice 50 years to grow. Okay, 50 years to grow. And we're going to see what our ending population will look like. So on my calculator, I'm going to do the exponent first. So 0.004879 times this by 50. So that's the way my calculator works. Enter. I'm going to take the exponential of that, which is 1.27, and multiply that by the 40,000 that we started off with. And the population of Coville in 2020 is 51,051 people. Okay. So we will end up with problems, not necessarily on this Excel, that we are going to have to work backwards towards to solve. We're going to be given an initial value, a final value, but they're not going to tell us our rate, and then we're going to have to find that rate ourselves. Okay, that's it.